Maybe you know. Science meets the questions you never thought to ask. In 1980, a physicist named John Anderson sat at the Jet Propulsion Laboratory in Pasadena, staring at two stacks of tracking data. Pioneer 10, Pioneer 11. Both spacecraft, billions of kilometers from Earth, were moving wrong. Not by much. A fraction of a hair width per second. But it was there, every year, for 3 decades. And no one could explain why two machines, hurtling toward the edge of the solar system, were quietly disobeying Isaac Newton. On March 2, 1972, an Atlas Centaur rocket lifted off from Cape Canaveral, carrying a 258-kilogram spacecraft no bigger than a small car. Its name was Pioneer 10. 13 months later, its twin, Pioneer 11, followed. Their mission was a kind of cosmic dare. Get past Jupiter. Survive the asteroid belt. See if a fragile bundle of antennas and isotope generators could endure radiation belts no human-made object had ever crossed. They did. Pioneer 10 became the first object to fly through the asteroid belt, the first to photograph Jupiter up close, the first machine ever launched on a trajectory that would carry it forever beyond the sun's grip. By 1979, Pioneer 11 had reached Saturn. By the early 1980s, both were sailing into the cold dark beyond Neptune, and NASA was tracking them every day, every signal, every microsecond. Because to navigate a probe 12 billion kilometers from home, you have to know where it is to within meters. The Deep Space Network listened. The math was clean. Newton's laws had governed every orbital trajectory for 3 centuries, until something started pulling the Pioneers slightly off course. John Anderson didn't set out to break physics. He was a navigator. His job at JPL was simple in concept and brutal in practice. Predict to within a few kilometers where the Pioneers would be next month, next year, next decade. He fed Doppler signals into supercomputers. He compared expected position against measured position. The numbers should have matched. They didn't. By the time the Pioneers passed Saturn, both spacecraft were drifting. Not sideways, not falling. They were decelerating, slowing down, by an amount the sun's gravity alone could not explain. The discrepancy was tiny, about 8.74 times 10 to the negative 10th meters per second every second, roughly 1/10 billionth of Earth's surface gravity. Imagine a leaf falling on Jupiter, but 100 million times slower. But it was real. It was constant, and it was identical for both spacecraft. Anderson and his colleague Michael Martin Nieto checked the data again and again. By 1998, after 18 years of tracking, the anomaly had survived every test. They published. The physics community read the paper, and the response was somewhere between fascinated and horrified. Because if the anomaly was real, something deeper was wrong with our understanding of the universe. Here's why the anomaly mattered. Newton's law of gravity is one of the most tested equations in human history. We use it to land probes on comets. We used it to put men on the moon. Every spacecraft that has ever maneuvered around a planet trusted that math down to the 11th decimal place. And it had never failed. Not once. So when the Pioneers started decelerating, you had 2 options. Option 1. There was a tiny error somewhere in the modeling. Maybe the spacecraft was leaking fuel. Maybe it was being pushed by sunlight in a strange way. Maybe heat was radiating off it asymmetrically. Mundane. Boring. Solvable. Option 2. And this is where physicists started losing sleep. Gravity itself behaved differently at the edge of the solar system. That would mean general relativity, Einstein's masterpiece, was incomplete. That dark matter, dark energy, the whole structure of cosmology might be built on a slightly bent foundation. Some theorists proposed entire new physics, modified inertia, extra dimensions, exotic particles. The Pioneer Anomaly became a small crack that some thought might split open the universe. 2 robots, 12 billion kilometers away, were quietly threatening to rewrite physics. But here's where it gets strange. If gravity itself was misbehaving past Saturn, then every spacecraft past Saturn should be showing the same drift. The Voyagers, launched a few years after the Pioneers, were also out there. Galileo, Cassini, Ulysses, all sailing in the same gravitational neighborhood. And when scientists checked their tracking data, nothing. No anomaly. The Voyagers obeyed Newton perfectly. So did everything else. Only the Pioneers were misbehaving. This was the puzzle that broke the new physics theory. If a fundamental force of nature had bent, it should bend for every spacecraft. Not just two. Whatever was tugging at Pioneer 10 and Pioneer 11 was specific to them. Something about their design. Something about their geometry. Something quiet, persistent, identical between two near-twin probes, and absent in every other vessel humanity had ever launched. For a while, that fact made the anomaly feel even weirder. Why these two, and only these two? Theorists started looking less at gravity and more at the spacecraft themselves. Engineers pulled out the original Pioneer blueprints, decades old, yellowed at the edges. The answer wasn't going to come from Einstein. It was going to come from a heat lamp. In 2004, a Russian-born physicist named Slava Turishev at the Jet Propulsion Laboratory began an obsessive 5-year project. He tracked down 30 years of telemetry, magnetic tapes, punch cards, handwritten log from JPL's basement archives. Some of the original Pioneer data had been almost lost. Turishev's team digitized it all. They reconstructed every transmission Pioneer 10 and 11 had ever made, from launch to silence. Then they built something unexpected, a full thermal model of the spacecraft, down to the rivet. Each Pioneer carried 4 radioisotope thermoelectric generators, RTGs, fueled by plutonium-238, producing about 2,500 watts of heat. That heat had to escape somewhere. Most of it radiated through the back of the spacecraft, away from the dish antenna, pointing at Earth. When Turishev simulated it, the answer fell out cleanly. The asymmetric heat, photons of infrared, leaving the rear of the probe, slightly faster than the front, was acting like a microscopic rocket. A push of 8.74 times 10 to the negative 10th meters per second squared, pointed back toward the sun. The exact number Anderson had measured 32 years earlier. In 2012, Turishev published. The Pioneer Anomaly was solved. Newton was vindicated. Heat was the killer. And just when you think the case is closed, there's a final wrinkle. The Voyagers carry RTGs too. So do Cassini and Galileo. So why didn't they decelerate the same way? The answer is geometry. Voyager's instruments stick out on long booms, breaking up the heat in every direction. The Pioneers were compact, simple, almost symmetrical, and that simplicity made the heat leak directional. The very thing that made the Pioneers' elegant engineering also made them unique physics experiments. Which raises a question scientists are still sitting with. How many other anomalies in our universe are not new physics, but something boring we missed? Spacecraft trajectories around Earth still occasionally show tiny unexplained kicks during gravitational flybys. They're called the flyby anomaly. We don't yet know what causes them. Some researchers wonder if they're another thermal artifact. Others suspect something deeper. Because here's the lesson the Pioneers taught a generation of physicists. Before you rewrite the laws of nature, check the wiring, check the heat, check the rivets. The universe almost never breaks. Our models do. And the difference between a revolution and a footnote can come down to where the photons are leaking. Right now, somewhere about 20 billion kilometers from Earth, Pioneer 10 is still drifting. It went silent on January 23, 2003, its last weak whisper of a signal arriving at NASA from a transmitter that finally ran out of power. Pioneer 11 fell silent even earlier in 1995. Both are still moving. Both are still cooling. The thermal force that fooled physicists for 3 decades is now too weak to detect because the plutonium has decayed and the rivets have grown cold. But the lessons live on every time we send a new probe. The OSIRIS-RX mission, returning samples from asteroid Bennu in 2023, used thermal modeling refined directly from Turishev's work. Future missions to Europa, to interstellar space, to the gravitational lens of the sun, they all have to model heat with new precision. Because we now know that a 1-watt asymmetry can change a trajectory by hundreds of kilometers over a decade. It also reshaped how scientists react to anomalies. Today, when a measurement disagrees with theory, the first instinct is no longer we found new physics. It's we forgot something boring. The Pioneers humbled us. their ghost still navigates. In 2012, Slava Turishev took the data Anderson had been staring at since 1980, and he closed the case. Two machines, billions of kilometers from home, had not been disobeying Isaac Newton. They had been radiating heat. That was all. A leaf falling, slower than gravity, off the back of a spacecraft. But for 32 years, the Pioneer Anomaly was a hairline crack in the universe. A whisper that maybe, just maybe, gravity wasn't quite what we thought. It pulled physicists down rabbit holes. It generated 200 published papers. It fed a generation of theories about modified gravity, about extra dimensions, about the dark structure of the cosmos. And in the end, the answer was photons. Heat leaking off the rivets of two old, small spacecraft. The universe didn't break. We just forgot how warm our own machines were. Two probes, still drifting, still cooling, still teaching. If you like this story, the next one is even stranger. In the late 1990s, NASA tracked a separate kind of anomaly, small, unexplained kicks that spacecraft receive every time they swing past Earth on a slingshot maneuver. We measured them on Galileo, on Near, on Rosetta. They're called the flyby anomaly. And unlike the Pioneers, this one, physics still hasn't solved. Subscribe, and we'll find out what's pulling on our probes. Thanks for watching. If this sparked a question, drop it in the comments. It might be our next video. We'll see you next time.